1.6 dependent events, so non-replacement and conditional probability. So dependent events is when one event influences the probability of another event. So let's go ahead and illustrate replacement and non-replacement items on tree diagrams. So a jar contains a red, a blue, and a yellow ball, and a student removes 2 balls, one after the other. So we're going to draw a probability tree diagram to illustrate and count the number of outcomes when. So the balls are replaced after each selection. Okay, so that would be independent, okay, replacement. And then we're going to do it with when the balls are not replaced after each selection, which is dependent, okay, non-replacement. So I already put in the tree diagram because this is what we've been working on so far. Okay, so red, blue, and yellow, each of these has a third probability of getting chosen. And for I, we replace the balls and then all the probabilities reset. Okay, so then the probabilities again are 1/3, 1/3, 1/3, all the way down. Okay, so the total number of ways here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1/3 times 1/3 is 1/9. So each of these outcomes has a 1/9 probability of happening. Okay, so we've seen that already. Now let's actually compare it to when we do not replace. Okay, so the first ball that we can pull out is red, blue, or yellow. Okay, these are definitely 1/3, 1/3, 1/3. What we have to think about is, so we have red, blue, and yellow. If we pull out a red and we do not replace it, we now only have blue and yellow. So we can pull out a blue or a yellow, and now that's 50-50. So this actually changes the probability. Even though we're handling the exact same set of balls, by not replacing our red ball after we pull it, the probability changes, and blue and yellow now have a 1 in 2 probability of being chosen. Okay, so likewise, if we pulled out the blue, we have a red and a yellow left. Okay, so red and yellow, and these are 1/2, 1/2. And if we pulled out a yellow, we can either pull out a red or a blue. And these again are 1/2, 1/2. So this time the total here, there are 6 different situations that we can run into. And if you think about 1/3 times 1/2, all the way down here is 1/6. Okay, so now let's do B. What is the probability that you pull a red ball followed by a blue ball? Okay, so with replacement. So B, probability of red, then blue. So we have this one way, which is 1/9. Okay, and for non-replacement, so probability of red, then blue, we have it here, and that's 1/6. So they can only happen one way, both of them. However, the denominator is 9 versus 6. Okay, there's just 6 less options that it could be. Okay, and remember this end total, really start to connect that like it matches up with the denominator. Okay, and now C. What is the probability when you pull a yellow ball followed by a yellow ball? Okay, so yellow, then yellow. So with replacement, we can get yellow, then yellow, 1/3, 1/3, and that's 1/9 again. However, the probability of a yellow, then a yellow, when we're not replacing, well, there are not 2 yellow balls. So if we take a look at yellow first, the only situations we have are red and then blue. So this is actually impossible. So that's 0 out of 6. Okay, because once we pull out the yellow ball, we don't have any yellow balls left to select from. Okay, example 2. A box contains 5 red, 3 blue, and 2 green marbles. You randomly draw 2 marbles without replacement. Okay, so that's big here. A, what is the probability that both marbles are drawn are red? So red and red. Here's the situation, okay? Originally, we have 5, 3, and 2, which is a total of 10. So 5 marbles out of 10. The issue is with the second draw, we now have gotten rid of one of the red marbles. So what we're going to do is instead of having 5 red, 3 blue, 2 green, we now actually have 4 red, 3 blue, and 2 green. That's what we have left. So what we're going to do is we're going to say, okay, well, we have 4 red marbles left, and the total here is 9. So it's not 5 over 10 times 5 over 10. It's now 5 over 10 times 4 over 9. Okay, and we can say 20 over 90, which is 2 over 9. Okay, let's go to B. What is the probability that the first marble is blue and the second marble is green? Okay, so going to the blue, that's when we reset all the probabilities. We have 3 blue out of 10 marbles. However, once we get rid of one of the blue marbles, we actually only have 9 marbles left. But we didn't get rid of a blue marble. Now we have, a green marble. Now we have 5 red, 2 blue, because we got rid of one of the blue ones, and 2 green. So that denominator of a 2 for the green still stays the same, but the denominator, we have 1 less marble. So we have 6 over 90, okay, and you can reduce it if you want. 1 over 15. Okay, and let's go C. What's the probability that at least one of the marbles is red? So we're either going to have something then red, or we're going to have red then something, or we're going to have red and red. Okay, 3 situations here. So let's actually, what we're going to do is we're going to regroup these. We're going to regroup it to, okay, we have 5 red, and we actually have 5 not red. Okay, so a not red one, we have 5 out of 10 times a red one, which is 5 out of 9. Now a red one first is 5 out of 10, and a non-red one is going to be 5 out of 9. Now a red one first is going to be 5 out of 10, but because we took out that red one, the numerator also goes down. It's going to be 4 out of 9. So we're going to have 25 plus 25 plus 20 over 90. Okay, so this is 70 over 90, which is just 7 over 9. Okay, now let's talk about product rule for dependent events. To calculate the probability of 2 dependent events, A and B, okay, occurring, what we do is multiply the probability that event A occurs, okay, which is right here, by the conditional probability that event B occurs given A occurred. Okay, so when we talk about this word given, we focus on that vertical line. So since the outcome event B depends directly on another event A occurring, so A would have had to occur. Okay, so this conditional probability equation is just the first one rearranged. If you think about like the P at A being in the denominator, if we divided both of these sides by P at A, that goes away, and then all we did was rearrange. So that's the same equation. Okay, let's get rid of that. Okay, so let's go ahead and use that equation. The probability that Crosby gets a goal and an assist in a game is 20%. So goal and assist is 0.2. Crosby gets an assist. in 75% of the games that he plays. So determine the probability that Crosby gets a goal given, so probability of a goal given he gets an assist. Okay, so I always remember this as whatever I'm given is going to be the denominator. So what we're going to do is we're going to do goal and assist in the numerator over the probability of an assist. That's what we're given. So we're going to go 0.2 divided by 0.75, and we get 0.2666, so 0.27. Okay, you can do therefore there is a 27% probability that he gets a goal given he gets an assist. Okay, now let's do conditional probability in the form of a tree diagram. Okay, a study of telemarketing companies' data shows that of 1,000 calls placed, okay, so n equals 1,000, that's like the number of trials. We can even say NT. The experimental probability of a call receiver staying on the line for at least a minute is 16%. Okay, so if you think about this, we can say, okay, at least a minute, so greater than or equal to 1 minute is 16%. Okay, on the flip side, we would say less than a minute is going to be the complement of 16. So if you need to go 1 minus 0.16, that's fine. But if you can do it in your head, that's also fine. Okay, the complement of 16 is 84, 0.84. These two add up to 100. Okay, now the conditional probability of a result or a call resulting in a sale. So there is a sale given that the receiver stayed on the line for at least a minute is 10%. So what we're going to do in this diagram is we're going to locate a minute, which is right here. And we're going to start there, okay? And we're going to say, okay, if this is where we are, okay, we're starting at greater than or equal to a minute, then I can say 0.1 end up in a sale. And as a complement, 0.9 end up in no sale. Okay, and then we can say no sales were made if the receiver did not stay on the line for at least a minute. So let's locate the less than a minute, and we're still going to have sale or no sale. But this is a little bit different. So the sale is 0. They're not making a sale if the person wasn't on the phone for at least a minute. But 1.0, so 100%, not making a sale. And still the 0 and the 1 add up to 100. Okay? So if we're at this situation right now, what I would do is I would multiply the 0.16 times 0.1. So probability of greater than or more or equal to a minute and a sale is 0.016. And then 0.16 times 0.9 is 0.144. And then 0.84 times 0 is obviously 0. And 0.84 times 1 is 0.84. And if you add these up, they should add up to 1. Okay, so 100% of the probabilities lie amongst these 4 different situations. Okay, so we created a probability tree diagram as we were actually reading. Okay, now use the probability tree diagram to state the probability of, okay, so this is going to be B, number 1, a sale given the receiver stayed on the line for at least 1 minute. Okay, if you think about this, if we're given this piece of information, we can actually start here. So we're given this, we start here, we ignore everything beforehand, and now we only have to look at the sale, which is 0.1. 0.1. Okay, now be number 2, probability of no sale, so sale complement, given the receiver did not stay on the line for at least a minute, so less than a minute. Okay, if you think about this, we are going to start here. We are given this piece of information that the person did not stay on the line. So no sale here is 100%. Okay, and then to expand this, how many sales were made? So if we actually take a look at sales, we can identify that, okay, sale 0.016 and then 0. So we don't have to pay attention to this one. We're just going to focus on the 0.016. So the expected number of sales is going to be the number of phone calls, which we read as 1,000, okay, times the probability of a sale. So altogether, the probability of a sale is 0.016. Okay, if you think about 1, 2, 3 decimals, 1, 2, 3 decimals. Okay, so we're going to get, I believe, 16. Yeah. So the expected number of calls or sales made out of the 1,000 calls is 16. Okay, last one. So we can also see conditional probability in the form of a table. Okay, so the table shows the results of a study in which researchers analyze the relationship between a child's IQ and the presence of a specific gene. Okay, so let's just go ahead and read the table. Okay, so we have gene present and gene not present. And then we have high IQ and normal IQ. So if we go ahead and total these, okay, we have 72, the gene is present. Then we have 30 where the gene is not present. We have 52 people with a high IQ, and we have 50 people with the normal IQ. Okay, adding down or adding across, you should get 102. Okay, after we complete all the totals, we should be able to go back to the questions and then just take a look at what we're given and work with these numbers. So find the probability that a child has a high IQ, so high IQ, given that the child has the gene. So here's how I would read this, okay? So if we're given that the gene is present, I'm going to focus on this blue section, okay? So every other person in this study, we can completely disregard. We are now just going to focus on the gene being present. That's out of 72 people. And now what's the probability that they have a high IQ? Well, you just have to read that. It's 33. So 33 out of 72. Okay? And find the probability that a child does not have the gene. So gene complement. So does not have the gene, given that the child has a normal IQ. Okay, so this is how we read the chart the next way. So normal IQ, I'm going to go ahead and do this with red. So we're restricting our people to these 50 people. So essentially, out of these 50 people, what is the probability that the gene is not present? I get 11.